Time crunch.
Time crunch? All right. Well, I told that the PAs don't be too picky, don't be too hard for grading, and try to get them graded very quickly so we'll get the results very soon. All right. Any questions before we continue from where we left off? So what we started to talk about was the following very important results. That under appropriate regularity conditions, the maximum likelihood estimate satisfies the central limit theorem. Root n theta hat minus theta converges to a normal of 0, and the variance is 1 over the Fisher information. I keep alluding to these regularity conditions. I even wrote them down. I was going to write them on the board, but they're really long, and I think it would take a long time. The most important thing is that the density is 3 times differentiable with respect to theta. So it's smooth. And that you can exchange derivatives and integrals, the derivative of the integral back. And so I don't see that there's much value actually writing all that out, but the important thing is to understand that there are conditions that are required for asymptotic normality. They're satisfied by almost all of the parametric models. No. The big exception is the uniform, because the range of the data there depends on theta. That's a big exception to all this stuff. And also that the number of parameters has to stay fixed. We'll deal with problems where that's false when we use the parameters. So we started to prove this, and let's just complete the proof. We started by saying, well, look, if I take the derivative of the log likelihood at the MLE, that's 0. It's a maximizer. And then if we think about this function as some smooth function that we're going to expand here. I'm going to expand it around the true value. I'm doing a first order Taylor series, and then theta hat minus theta. And the second derivative at the true value. And we'll just stop there and say this is approximately equal to. So making this rigorous, which is quite a bit of work because you have to actually show that the remainder is small. Then I rearrange this, and if I just rearrange it, what we get, the way I wrote it was root n theta hat minus theta, this is where we left off, is approximately equal to 1 over n. 1 over root n times the score, and minus 1 over n times the second. And I call this A over B, so we can examine the numerator and the denominator separately. So let's take a look at the numerator. The numerator is 1 over root n, the derivative of the log likelihood. The derivative of the log likelihood, well, that's just the definition of the score function. And of course, the derivative of log p, the joint distribution, because we're assuming IID, it's just the sum of the log for each observation. So in other words, this is the sum. This is really just the sum of the score xi. Okay, let's call it xi. What I mean by that, it's just the derivative of theta log. And there's a 1 over root n here, although I'm going to write that as 1 over n times root n. Now, one thing we saw about the score function was that it had mean 0. So I'm actually going to write this as, this might seem kind of useless, but I'm going to write it that way, just to emphasize it's something minus this mean. And in fact, what have I got? If I call the average of these are just IID random variables. So we could write this as root n, let's call it S bar minus its mean. S bar just being another way to write the average of And I'm writing it this way because you can see now it's an average of IID random variables minus mean times mean. Again, we know about the central limit theorem. It's just a sum, or an average. So by the central limit theorem, we know that this converges to normal, mean zero. And then what's the variance? Well, it's just the variance of one of these guys, right? It's just the variance of one of these things. Well, what is the variance of that? Yeah, it's the definition of the Fisher information based on a single observation. So this converges to a normal with mean zero and variance I. Now, in general, if I have a random variable which is normal 0 sigma squared, I can write this. If I have, let's say this, I have some variable which is this. I can always write that as y equals sigma z, where z is standard normal, right? Because then this is mean zero and the variance would be exactly sigma squared. So I can always write a general normal as its standard deviation times its standard normal. So I'm going to say this is equal to, if I were to write this as square root of I times standard normal. So in some sense, what have I got? I'm going to say this is converging. I'm just on the numerator, the square root of I theta times the standard normal. How about the denominator? The denominator, well, that's just an average. The denominator is minus 1 over n. But of course, L double prime, that's the second derivative. What is L double prime? It's the second derivative of the log likelihood. But this is a sum over the observations, this is IID, and I can exchange the second derivative with the sum, so it's just the sum of the second derivatives. So this is the sum of the second derivatives, and this is 1 over n times the sum. It's just an average. So this is, by the law of large numbers, this is an average. This is converging to that average, and there's a minus in front. So this is converging in probability to minus the expected value of the second derivative But we saw that another way to write the Fisher information was precisely minus the expected value of the second derivative of the log of the density, right? That was another identity, that this is pi and theta. So this is converging in probability to a constant. The top is converging in distribution, the bottom is converging in probability. By Slutsky's theorem, the ratio is converging in distribution. So this becomes pi, which is z over the square root of I. And of course, this is just normal, mean 0, and the variance of this is 1 over pi, which is exactly what we set up to prove. So now you see that all those things, like defining the score function, defining the Fisher information, proving all those identities that the mean of the score is 0, Fisher information can be written as the expected value of the second derivative, all that wasn't arbitrary. It was because once you do all that definitional stuff, the proof really becomes quite simple. And these quantities just arise naturally. They're not just pulled out of thin air. So that's pretty good. We know quite a bit now about the, let's rewrite that result, because we know quite a bit about the maximum likelihood estimator. If I rewrite this in the informal way, that's saying that theta hat is approximately normal, centered at the truth, with variance 1 over n. And remember, n times the Fisher information is the same as the Fisher information computed from n observations. And this tells us something very important. If I want to know what's the variance of my MLE, at least this is an approximation, but it says that the variance is approximately equal to this. And hence the standard deviation, or standard error as it's usually called, that's just the standard deviation of an estimator, which is the square root. Is approximately, I should say, the square root. Now what do you do in practice? We don't know theta. But again, by Slutsky's theorem, I can put in an estimate of this, and the ratio is going to 1 in probability. So what ends up happening in practice is people use the estimated standard error, which is simply the Fisher information evaluated at the MLE. That's a consistent, as long as the Fisher information is a smooth function, or a continuous function, then by the continuous mapping theorem, theta hat converging to theta will imply this is a consistent estimate of the standard error. And it doesn't change its limiting distribution. Another way to write this again is to write this as n times the Fisher information based on one observation and multiply it by n, either way. This is the most common method in science of computing standard errors of estimators. Almost all scientific reports in biology and physics and so on, they include estimates of quantities and they include standard errors, and they're almost always this quantity. So this is a very, very, very commonly used approximation. It is an approximation, but at least in low-dimensional problems, it's a pretty accurate approximation. We'll talk about more. There are more exact ways to do things that we'll talk about when we get to confidence intervals, but this is pretty common. So a very common thing, we report an estimate, often the maximum likelihood estimator, and standard error, or its approximate standard error, which will take this form. So let's do a couple of examples of this. Oh, actually, before we do that, let's talk about the, to remind you about the delta method. Any questions about this before we move on? Remember that we might not be interested in theta, we might be interested in some function of theta, let's say tau theta. So that's easy to deal with. The maximum likelihood estimator of this is just tau theta hat. And remember what the delta method says. It says that a smooth function also then, it inherits the central limit theorem. The only difference is the standard error, or the standard deviation, sorry, in this case the variance, is going to involve the derivative of that function squared. Now what that means then is that when you compute the approximate standard error for a function, let's call this tau hat. All you have to do is take the derivative of that function so not only can we get the MLE for the parameter, we can get the MLE for a function of that parameter, and we can get the standard error for the MLE of the original parameter or the function of that parameter. So let's do a few examples of this to make sure this is clear. So I'm on page 10. So let's suppose we have x1 to xn an exponential distribution. We don't really use the exponential distribution very much. What is the exponential distribution? It's just this family exponential distribution comes up a lot in lifetimes of things like you say, how long does a transistor last before it burns out, or a light bulb? It's often the case that for things like that, they follow approximately some sort of exponential distribution. So that type of analysis, you often see this distribution coming up. Again, it's a family. So let's go through all the calculations. The log likelihood, I have to multiply this n times, so I'm going to get theta to the n. e to the minus n theta x bar. So the log likelihood minus theta x bar plus n log theta. Take the derivative, I get the score function. And so if I set this equal to 0, and you can check that that's the unique maximizer, we get that the MLE is 1 over x bar. I should warn you that some books write the exponential distribution differently. They use 1 over theta here and x over theta. That's just another parameterization of the exponential distribution. It doesn't matter which one you use as long as you use the same one consistently. So in our case, the MLE is 1 over x bar. If you parameterize it the other way, the MLE would just be x bar. So that's, okay, that's great. That's pretty easy. You can now take the second derivative of this. It turns out, if I did this right, it's minus n over theta squared. There isn't even a random variable in this case in there. So getting the Fisher information is pretty easy. Take the minus the expected value, but there's nothing, there's nothing random there. So that's this. And so there we go. We get that the MLE is approximately normal, mean theta, invariance, theta squared over n. Or more formally, root n theta hat minus theta converges to a normal distribution. What that would mean in practice is if I wanted to know the approximate standard deviation of this thing, it would be theta hat over root n. Soon we'll see there's an even easier way to get these standard errors, not to do any calculus at all, but for now we're doing it this way. Let's go back to Bernoulli. We worked out the Fisher information and the score functions for Bernoulli previously. So we know that the MLE is just x bar. I'll just remind you, what did we find? We found that the Fisher information is this. So that tells us that this converges to a normal, 0. Now, we didn't need to know maximum likelihood to know this, but I could have just said, here's an average of some random variables. What's the limiting distribution? Well, in this case, the MLE is just an average, so we could just directly apply the central. So we didn't really need it here. The usefulness of this is that sometimes the MLE will be a very complicated nonlinear function. That's really when it comes in handy. So here I used the Fisher information on that, but I didn't really need to. At any rate, this gives us the estimated standard error, which is p hat 1 minus p hat over n. And let's just pick a function. Let's suppose we were interested in, say, p over 1 minus p. Let's assume p is not 0 or 1. So all we have to do to deal with this, we know what tau hat is. It's p hat over 1 minus p hat. And the derivative of that function with respect to p is 1 over 1 minus p squared. So therefore, the approximate standard error, tau hat, is the original standard error. So here's what you do. You take the original standard error times the absolute value of the derivative, 1 minus p squared, which is p hat So here's where the limiting theory comes in kind of handy. Because although I could have gotten the limiting distribution of x bar directly, when I ask you what's the limiting distribution of p hat over 1 minus, that's, if I tried to get the exact distribution, for example, that would be very, very complicated. But approximately, it's normal, and the standard deviation is given by this approximation. So there, again, is the usefulness of the delta.
There is a typo. When we define the new standard error according to Cal, we're putting the absolute value of the derivative inside the root, but I think it should be outside of the root.
You're right. Where did I do that?
Just when you were
You're right. The bottom of page 9.
Yeah.
Yes, that should actually. Thank you very much. That should be. If I'm going to put it in the root, there should be a square on that. So where is that? At any rate, I can't find it where it is on the board, but that's correct. So I should either have made it square or taken it outside of the root. So the very last equation on page 9, thanks. The way to deal with that is there should be a square if the derivative is on the inside of the root. Okay. That's the variance has the square on it, not the standard root.
Can you write that on the board? Just to make
Yeah. So here it is here. It's the standard error should be square over. That's the variance. Yeah. Okay, let me now say a few words about the optimality of the MLE. Fisher claimed many years ago that the maximum likelihood was in some sense the best estimator. And it wasn't long before people came up with counterexamples to show that there was estimators that in some sense could always do better than the MLE. And in complicated models, that's not surprising, but even in one parameter well-behaved models, people apparently came up with estimators that in some sense could beat the MLE. But these estimators had a weird property that they were sort of unstable estimators. So in our advanced statistical theory course, we talked about this in a lot of detail because it's kind of complicated. But so I'm not going to go into the details. Let me just say that there is a theorem that says in these finite dimensional models with all these regularity conditions, if you assume that you're dealing with an estimator that is what we call a regular estimator, basically it means it's a well-behaved estimator in some sense, then it's not just the MLE that's going to have a normal limit. In fact, what's going to happen is this. Any well-behaved estimator, let's call it theta swivel, is also going to converge to a normal, which means 0 and some variance via theta, but it's always going to be the case that this is bigger than or equal to the variance of the MLE. This is something that was proved by Lacan in maybe say the 70s or 80s. It's surprisingly difficult to make this precise. I mentioned a reference in the previous lecture by Van der Waart. If you want to see the details, that's a really good book to look at. I'm just going to state this informally. So this result is saying that we know the MLE converges to, let me call this twiddle, so that the MLE converges to normal of mean 0, 1 over Fisher. Other well-behaved estimators will also converge to normal, but their asymptotic variance will be larger. And that's the sense in which we mean the maximum likelihood estimator is optimal. We say it's efficient. It has the smallest possible variance of all well-behaved estimators. This is the reason why people use the MLE. There's no philosophical reason for using the maximum likelihood estimator. It's strictly a pragmatic thing that its variance, or at least its asymptotic variance, is small compared to other estimators. And so that's what makes the MLE so popular. Although, as we'll see when we get to more complicated models, that's no longer true. This is, again, in the world of sort of finite dimensional world models. So there's a small section there called efficiency which talks about that.
It doesn't need to be a well-behaved estimator.
Well, I was trying to avoid describing that because it's somewhat complicated.
Sure.
It has to, it's basically, you don't want estimators whose behavior is very sensitive to small changes in the parameter, because those would be very non-robust estimators. So those are called regular estimators, and it takes quite a bit of technical apparatus to describe all that, and it's really not a path we want to go down here. So look at the book by Van der Vaart if you are interested in that, because he explains it very nicely. But be prepared, it's a long, it's chapters and chapters of preparation to get to that result. So it's not something you're going to read in 5 minutes. Okay, any other questions? All right, so there is this kind of important result saying something about the MLE being optimal. This asymptotic theory, so far, then, is useful for several things. One is it gets us, we've learned something about the approximate distribution of the estimator. That's going to be useful for lots of things. We know something now about the optimality of the estimator. It's also a way to compare estimators. And this is called relative efficiency, which is, suppose I do want to compare two different estimators. There may be a reason. There may be reasons for using other estimators besides the MLE, despite the fact that it's in some sense optimal. Other estimators may be easier. A perfect example of this is in some people use method of moments estimators now for pretty complicated models because they're much easier to compute than the maximum method estimator. So you might want to know, if I use some other estimator, how much am I losing? And so a natural way to compare that is, suppose you have two different estimators. Suppose they are both, let's call them well-behaved. In the sense that they both have asymptotic normal distributions. So I'm just calling these two arbitrary things W and D. Asymptotic theory gives us a way to compare how much you're losing by using one estimator versus the other one. So people call this the asymptotic relative efficiency, which is just the ratio. So let's see, I always get confused about which way I put the ratio down. So if this is big, then that means this has a big standard deviation compared to this one. And so this is telling, and vice versa, obviously. So this is telling us, so, if that's 0.7, it's sort of saying, well, one of them is like 0.7, 70% as efficient as the other one. And it's actually quite a useful way to sort of say something precise about how many, it's like saying one of them was worth 70% of the, is using 70% of the data compared to the other one. There's no way to think about it. So I thought I'd do just a very simple, specific example so you can see how this kind of calculation is done. So this is example 17 here. So let's look at the Poisson. So a good exercise would be to go through and convince yourself you know how to compute the score, Fisher information, and all of that stuff. We know the MLE is X bar. Okay. Now, suppose I don't want to estimate lambda, but I want to estimate e to the minus lambda. Now, why would I even be interested in that function? Well, that actually has a very well-defined meaning, because let's suppose what we're counting here is the number of times your computer network crashes per week or something like that. Let's say that's Poisson. I don't know if it's Poisson, but maybe say Poisson. And I want to know what's the probability we get through the whole week with no crashes. That is, what's the probability x is equal to 0? Well, in a Poisson, you look at the, what's the formula for a Poisson? The probability x equals to x is e to the minus lambda to the x over x factorial. And in particular, the probability x is equal to 0 is precisely e to the minus lambda. So the probability that your network's not going to crash is e to the minus lambda, so that's a very meaningful parameter. Now, here's a couple ways to estimate it. One of them would be the MLE. So what's the MLE? Oh, that's easy. But somebody could come along and just say, I have another way to estimate this. We just look at past weeks, look back last 20 weeks, and just say every week, did it crash or not? So in other words, what you do is you create a new random variable, which is an indicator function. for whether x is 0 or not. Just how often did the system crash in the past? I mean, go through a whole week without crashing, is what I should say. And why don't I just take the average of those? After all, what's the expected value of this? The expected value of this is the probability that x is equal to 0, which is precisely this. So by definition, this is an unbiased estimator if I call this one W. So right away we see this is an unbiased estimator. It's equal to tau. And it's an average. So it has a central limit. Yeah, I can just compute the limiting distribution, right? It's just a normal. That's the mean. I can compute the variance directly. So let me just record what's going on here. The MLE, the MLE, how would I get the limiting distribution? Well, I would first get the limiting distribution for lambda. We know that the variance is the Fisher information. Now I'm just taking a function of that, so I use the delta method. So that's a good thing to do at home. Make sure you know how to do this. Be a great next question. This is what I get from the delta method. On the other hand, again, I could just directly do the central limit theorem here. Just compute the variance. Yi is not hard. This is just a Bernoulli. It's either 0 or not. And probability of success is tau or 1 minus tau. So I get immediately that this estimator converges to a normal, mean 0, and that turns out to be e to the minus lambda, 1 minus e to the minus lambda. And now the asymptotic relative efficiency, I can get this by taking the ratio of those two variances. So just imagine actually doing this for a long time, and you get your estimators and your friend gets his or her estimators, you look at the histograms, what you're going to see is they're both normal, they're both centered approximately at the true value, but your friends would have a wider spread. And the ratio of this tells you how much wider. If you work the ratio, then is the asymptotic relative efficiency is lambda over e to the lambda minus 1. And we know that has to be less than or equal to 1 because the MLE has the smallest variance. And so now what you could do is, I mean, it depends on lambda, but you could try out different lambda values and say how much efficiency am I losing by using my friend's estimator. But here's the thing, your friend's estimator, you're kind of laughing at your friend saying, well, I know that mine has better asymptotic relative efficiency. But can you think of a reason why you might want to use your friend's estimator instead of the MLE? It's unbiased, that's one thing, although unbiased is not necessarily the most important thing, but that is true. Computationally, no, they're both pretty easy. But I would say that your MLE, this result, all depends on the model being correct. The idea that yours has better asymptotic relative efficiency than your friend's. If the model's wrong, suppose it's not Poisson. You did everything assuming Poisson, but your friend's estimator kind of makes sense in a non-parametric sense, we'll say. I'm getting ahead of myself, but look, if I just count how often the network didn't crash, without even assuming Poisson, it just seems like counting those things might be a reasonable way to estimate it. In fact, this is consistent because it's unbiased, and the variance you can see is going to 0 without even assuming Poisson. We have a consistent estimate. So there's a bit of a trade-off here, and this is something which happens all the time in real life. It's easy to say, I'm going to assume a model and get the MLE, and I can prove mine is better because that asymptotic relative efficiency favors the MLE. But always keep in mind that's only true if the model is correct. The other estimator might be still valid under wider conditions. You're sort of trading off robustness for efficiency. And this is something that happens all the time. You have to really decide how much you trust the model or not. If you really didn't trust that Poisson model, then you might be better off using that other estimator. So I just want to temper the claims that the MLE is optimal with a bit of pragmatism. That claim really should be if the model is correct, the MLE is optimal. And that's a really important qualifier. All right. Everything I've said so far has been actually for scalar parameters, and it all generalizes to the multivariate case very simply. I'll just state the result. We won't prove it again because the proof's basically the same, but now suppose that theta is a vector of parameters. But this is important. The dimension of that vector we're assuming is staying fixed. It's not increasing with n. Then once again we get that this converges to a normal. Remember, these are vectors. And so it's going to converge to a multivariate normal. So a normal of mean 0. By 0 here I really mean, well, right up, a vector of zeros. And instead of 1 over the Fisher information, remember in the multivariate case you have a Fisher information matrix. So what takes the place of the 1 over the Fisher information is the inverse of the Fisher information matrix. Okay? And actually from this, if you're interested in a particular component, say you wanted to know what's the standard error of the third component of that. Well, all you have to do is take this inverse Fisher information matrix and read off from the diagonal the corresponding element. That's the standard error. That gives you the standard error for that particular element. Okay, so the approximate standard error for the jth element, let's say, you just simply take the inverse Fisher information, you take the jj element, so all the information you need is still there in that matrix. It's just that now we have to look at the diagonal matrix and pull off the appropriate entry. And in fact, you can still do the delta method because we saw there was a multivariate delta method. So if you had tau now, let's say as a function of theta, and let's say a real value function. So it takes the entire vector but computes a scalar quantity. Then again, we get the delta method. So root n tau hat minus tau converges to a normal mean 0. And remember, what happens is you get the gradient. This is a vector. This is the gradient transpose y inverse times the gradient. So this is a number now. This is just a single number. So if I ask you, what's the MLE in the normal of, let's say, mu over sigma, no problem. The MLE is this. How do you get the standard error? Well, just think of this as a function of mu and sigma. And compute the gradient, the derivative with respect to mu and the derivative with respect to sigma, and then just multiply it by the inverse Fisher information matrix for the parameters. And now you get the limiting distribution for that particular function of the parameters. So there's a lot of information there contained in that Fisher information matrix. In a lot of computer software, that's what it's doing when it's giving standard errors, is it's computing this matrix, it's converting it for you, and so on. That's what comes out of a lot of statistical factors. All right. So, any questions? This is a good time for me to just briefly mention something. Some courses put a lot of emphasis on this. I just sort of mentioned it in passing. I feel it's sort of less important these days than it used to be, but I'm trying to figure out when was the right time to mention this. And I don't know, somehow arbitrarily I decided this was the time, which is, you may have noticed, a lot of our parametric examples, somehow, except for the uniform, most of them have this really nice behavior. Everything always sort of works out nice, and things just work well. And it's because a lot of them have this form, that they can be written in the following form. They're called exponential families. Exponential families. Not to be confused with the exponential distribution. It's got nothing to do with that. Although the exponential distribution is an example of an exponential family. But an exponential family just means that you can take the probability function or the density function and rewrite it as some function of theta, some function of x, and then e to the theta transpose t of x for some function t of x. So you can rewrite the normal this way, but it's not, here's a good exercise. Try to rewrite it that way. You have to exponentiate a bunch of stuff and combine a bunch of stuff. It's not always completely obvious. Same with the croissant. Try it with the croissant. You'll be able to do it with everything we've done so far except for one. The uniform, you will not be able to rewrite this way. The uniform is always the kind of counterexample. So the binomial, it's just a matter of, and it's not unique, right? Because suppose h of x had a 2 in front of it. Well, do I count the 2 as part of h of x or part of c? It doesn't matter. The key part is this, and you can write it as the parameters times these functions. So every probability, every family of distributions that can be written this way is called an exponential family. They have all kinds of nice properties. If you take the log like this, so take the like and multiply it, take the log and set it equal to 0, you'll see that the MLE comes down to solving the following equation. The expected value of x so that's an equation that pops up a lot, and the reason why I'm writing it down is it kind of unifies things a lot. When you keep computing the derivative of a like and set it equal to 0, maybe they start to look kind of familiar. You're always actually writing down this equation. And here's another thing. The t, remember, is a vector in general, but notice it has the same dimension as theta. And in fact, this is a minimal sufficient statistic. And in particular, it has exactly the same dimension as the parameter. This is a property of exponential families. That if you have a 3-dimensional exponential family, the minimal sufficient statistic is also 3-dimensional. It's not an accident. This is a property of these things. And there's lots of other properties about them, like you can check that the Fisher information, just by doing the calculation, turns out to have a special form. It's actually equal to, I'll write the scalar version. It's a double prime of theta, or a theta is equal to minus log of the c. So, why does this matter? Well, I don't know. Just a lot of theorems in mathematical statistics turn out to be easier when we deal with exponential families. And some books even have a special section where they just talk about exponential families, and they restate the asymptotic normality of the MLE because you can prove it more directly. There's all these nice things that happen when it's an exponential family. I don't put so much emphasis on it just because I don't even like putting so much emphasis on parametric families to start with. I'm always anxious to get through this and get to the real stuff, which is non-parametric statistics. So I don't put a lot of emphasis on this, but I just feel like I wouldn't be doing my duty if at least I hadn't mentioned it, and you'd never heard of an exponential family. You know, somehow people would say, you took that course in mathematical statistics and you never heard of what an exponential family was. So now you can say, I mentioned exponential families. And if you ever decide for your work they're important, you've heard of them and you can go look them up. We're not going to really spend any time on it. Okay, another thing I wanted to mention that I'm not going to go into detail, this is section 10 and 11 of the notes. So you can consider these, especially section 11, you can put a star next to it, which is everything I'm telling you about parametric families, as I just mentioned, is always under the assumption that the parametric model is correct. And here's the thing. The parametric model is never correct. I can't think of a single real example in real life where anybody would believe the parametric model. It's sort of a working model, but nobody actually believes they're exactly correct. And so, what do you do about that? Well, there's two ways to deal with it. One way is to get rid of them, which is what we're going to do shortly in a few lectures. But there's another route, which is called robustness, which is sort of try to find estimators which allow for deviations from the correctness of the model. So if you want to see a calculation like that, this is section 11. I'm not going to go through it, but let me just tell you what's in this example. As I just look at the normal, stick the normal model, And if I asked you, how do you estimate the mean theta? Well, from maximum likelihood theory, we know the answer. X bar. But if you've actually analyzed real data, you know real data is never normal, and in particular there's almost always outliers in the data. These are extreme observations. You know, people record numbers wrong or whatever you're doing, there's numbers get messed up. And so a very common thing in practice is don't use the mean, use something more robust like the median. Just take the, sort the data and take the middle value, the median, which I call, what do they call the median? I call it and there's always a trade-off here. So what I did in this example, if you want to look through it, is I actually worked out for you the asymptotic relative efficiency of the median to the mean. So what I did is I said, suppose the data really were normal, then we know from theory that this has to be better than this. And I worked out the efficiency, and it turns out to be 64%. Okay, so if you want to see the calculation, by all means, look through it. What does that mean? It means that if the data really are normal, my friend is using X bar, I'm using the median, it's almost like I'm only using 68% of the data in some sense. Because my variance is much wider than his variance. But if the data are not normal, and in particular if there's outliers, I'm probably going to do a lot better than he is. And that's because the median is much more robust. And you can see that informally, that if I take one observation and shoot it way off to infinity, that's going to have a horrible effect on the mean, but not on the median. Okay, so there's a whole branch of statistics called robustness that deals with this, trying to find robust estimators, and it's always this thing of trying to trade off robustness with efficiency. And so this example is in there just for those of you who are curious to see how you might do calculations like that. It's interesting because this was a very big area in statistics in the 70s and 80s. Then it kind of, people didn't pay as much attention to it. But now that we're in the era of big data and high dimensional data, people are interested in it again because when you have high dimensional data and big data sets, you're not going to look at the data and find outliers. It's just not possible. So trying to find robust methods is something that people have a renewed interest in these days. And not a lot is known in the modern setting. I'm not going to go into robustness though because it's quite a large topic in and of itself. It's another one of these things that I wanted to at least make sure you've heard of. The way we're going to deal with all this, and starting in a few lectures, is we're going to just use non-parametric methods. We're going to start talking about methods, maybe in about a week or two, that don't rely on the assumption of a parametric model. Those are called non-parametric methods. We still have a bit more to do on parametric methods before we get to that. But again, I just wanted to make you aware of that stuff. So, all right, so where are we? So we are still in parametric land, okay, for a few more lectures. And now, everything we have talked about so far is how do you find a good point estimator? A single estimator. And now we've seen quite a bit on that. The next topic we're going to do is hypothesis testing. I'm sure we've all heard of hypothesis testing. And this is something like, I want to test if the hypothesis that theta is equal to 3, or something, some specific hypothesis. There's a lot of controversy, even in like the New York Times, we've done about hypothesis testing, and rightly so, because for me, I think really I see hypothesis testing for us as a bridge. We're going to do that, and then we're going to do confidence sets. Confidence sets, in my opinion, are the most important part of statistics. And these are just sets. Instead of providing a single estimator, we're going to provide a set and say this set is a 95% chance of containing parameter. They're much more informative than point estimators because it tells you something about, is it a precise estimator, is it an imprecise estimator? And I like to think of hypothesis testing as kind of a bridge to confidence sets. In fact, the way confidence sets are constructed relies heavily on the theory of hypothesis testing. But this is not something itself that one should always use. In fact, there are certain cases when hypothesis testing makes perfect sense. Very specific scientific hypotheses. So for example, remember a couple of years ago there was a lot of news about the discovery of the Higgs boson, one of the biggest discoveries in particle physics. There was a very, very specific hypothesis. you know, there was, the null hypothesis is there's no bump in this spectrum or whatever at this point, and the alternative is there is, and there was a definite physical scientific hypothesis being tested, and the hypothesis testing framework that we'll talk about on Wednesday makes perfect sense there. But there's a lot of abuse of hypothesis testing. People do hypothesis testing when they really shouldn't be doing hypothesis testing, and that's something we'll talk about because it's something that, like I say, it's even in the news all the time. So for us, really, I really want to give you the big picture before we jump into the theory on Wednesday, which is, I'm not teaching you this so much because I want you to go out and do a bunch of hypothesis tests. It's really a mathematical bridge to confidence sets. Okay, so we'll start to cover this on Wednesday, and once we cover this, this will be very easy to cover. This will be very easy. Question? Yes? No, there's questions. Anybody have a question? All right, good. So then I'll see you on Wednesday.